Welcome to the Cosmic Pie Podcast, episode number 34. I'm your host, Wayne Barkhouse, and with me today is
Robert Moore.
And Robert, today we have a very special guest, which we'll introduce here in a second. For those of you who've never seen this podcast before, we are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. And just to remind people, we do have a live chat that's running, so if you have any questions at any time or any comments, please feel free to use that feature. Also, as a disclaimer, Robert, let's get that out of the way starting up.
Absolutely. The opinions we express are ours and ours alone. They don't reflect the opinions of the state of North Dakota or the university or the college or any of that sort of thing.
So please don't fire us. That's all we ask.
Right. That's what it boils down to.
Okay. Now today, our very special guest is Vincent Ledvina, who's at the University of Alaska in Fairbanks. Now, Robert, we think it's cold in Grand Forks. We'll have to ask Vincent what it's like currently in Alaska.
In Alaska, yeah.
I'm always curious about that. Now, Vincent has a very special tie with the University of North Dakota and with our Department of Physics and Astrophysics, because he is a former student of ours. So, Vincent, how are you doing today?
Doing great. Thanks for having me on.
So, Vincent, we miss you. we love
I miss you too.
we love having you here, Vincent, to be honest, and we're really proud of what you have accomplished. But for those of you who don't know you or what you do or you're involved in, you want to give a sort of an introduction to yourself and what you're up to?
Sure. Yeah, of course. So my name is Vincent Ledvina. I am a current graduate student at the University of Alaska Fairbanks. I'm originally from the Twin Cities in Minnesota. I chose to go to school at the University of North Dakota for my bachelor's in physics all the way back in 2018, and I just graduated last year. I chose, we can get into this later, but I chose UND because it was a place where I could see the auroras, and I'm a huge aurora chaser photographer, and also got into the science of it, which is what I'm pursuing here up at UAF. So UND was great to me. Made a lot of really great memories, and now I'm up in Alaska, studying the auroras full time, going for my PhD. And yeah, like you said, it's cold in North Dakota, but it's a little colder here. So I think we have you beat on that.
Now, Vincent, for those who don't know, because we have, a different level of expertise and background who view this podcast. So when you talk about aurora, you mean the Northern Lights, of course. And so what got you interested in looking at the Northern Lights? Is that something you had as like a child that you're interested in that?
Yeah, exactly. So back in 2003, it was October 30th and 31st of 2003, there was a really, really big geomagnetic storm, which caused auroras to move down. Usually they're in the polar areas, sort of around Canada, Alaska, and places like that, caused them to move all the way down to the mainland US. And I was only 4 years old, but I remember coming back trick-or-treating, and I actually saw them, the auroras, the Northern Lights, dancing in the sky. And that really inspired me at that young age. I didn't really know what they were, but I later learned on the TV that it was the Northern Lights that I saw that night. And obviously I didn't go out and, started to learn the science behind the aurora at 4 years old. But I think that experience sort of embedded this latent passion for this science and this phenomenon that then, came back when I was around 15 or 16 and starting to think about what I wanted to pursue as a career. Always been really into space, the outdoors. I was in Boy Scouts, so I was always outside camping. I got into photography, and then sort of everything just kind of came together when I was in high school, and I realized, hey, I can take photos of this thing called the aurora. And then it became sort of a game, because you can't see auroras all the time in Minnesota or in North Dakota. You have to do what's called aurora chasing, which means, reading the data, learning the science, and figuring out when these things are going to happen. So it became a challenge for me and a fun little, game for me to play to see if I could actually capture them. So that's what led me up to UND, was that the further north you get, the better your chances are. So, and my parents didn't want me to go all the way to Alaska. So UAF was actually on my list for my undergrad, but they wouldn't let me move 3,500 miles away, which is fair. So I chose UND as sort of a, stopping point, which I then used to go to UAF. But I've always been into the aurora. I was inspired as a kid. I feel like that's such a common thread with physicists, is some sort of childhood memory of gazing at the stars, or, stargazing and enjoying the night sky. But yeah, I've just always been into it my entire life, and it's really guided my path and my career and hobbies and everything else.
Now, Vincent, did you know there's a very famous person, at least the last name is person, that studied aurora? I mean, she has passed away not that long ago, just a year or two ago.
Hmm.
No,
Yeah, so
Baffling me
see if
too.
you see the last, you'll know the last name as soon as I say it. The last
okay.
name is Feynman.
Oh, yeah, really?
Yeah, so Feynman, Richard Feynman's sister, I believe her
Hmm.
name was Joanne Feynman, if I'm not mistaken. She actually spent her professional career studying the aurora.
I did not know that at all,
Yeah,
actually. I'm
yeah.
surprised.
And I figured
Wow.
we've got some people already going, how could there be that much to study about lights in the sky? But, yeah, there's quite a bit of interaction that goes on there.
Now, Vincent,
Yeah,
when you study aurora, the northern or southern lights, because we do have the display, around the South Pole as well as you mentioned around
yep,
the polar regions. So, maybe to try to explain to people, a lot of times when aurora, you can see them in the sky. If you lived in an urban environment, you may not necessarily see that. So somebody would see on TV, oh, there's a big display going to happen tonight, and they get out there and look from downtown, some city,
yeah.
and they're disappointed because they don't see anything. So you want to make some comments about that aspect of it.
Yeah, that's a really good point. So, I mean, the auroras happen in our atmosphere, but you can almost treat them as if they're, at the same point as stars, right? They're above the clouds and they're pretty faint. So you have to try and get out of the city if you want to see them properly. When there's a huge display, it's possible to see them. Like I've seen them in downtown Grand Forks, but that was under some really extreme activity. So,
Right.
in order to catch the really faint displays, you want to try and get out of town to an area with less light pollution. So cities and street lights, cars, anything that has a light outside casts, light in all directions, including up in the sky. And when you have these urban areas, essentially you have this light pollution bubble that goes out in all directions. So the further you can get away from these cities, the better. And
Yeah.
ideally, you want to go north if you're in the northern hemisphere. If you're in the southern hemisphere, you're looking south to see the southern lights. But here in the northern hemisphere, you want to try and go north out of the city, because if you go south, well, your city that you just drove out of is going to be in your way now, facing north. So you want to try and go north, or east or west works as well. But
Right.
yeah, definitely getting out of the city is important. People forget that sometimes. So
Yeah.
next time there's a chance to see auroras, you want to get as far away from civilization as you can.
That reminds me of the first time I ever saw aurora, and it wasn't when I moved to North Dakota. I was living in a small town in the western outskirts of Atlanta, Metro Atlanta, and
Oh,
we got to see some red aurora down that far south, and that was pretty neat. I even got an NPR interview over it because I was one of
wow,
the few astronomers down that way that got to see them. So they
that's cool.
were grilling me about what caused them and everything.
Yeah, and I guess you could use sort of a rule of thumb. If you look out from wherever you live, from your backyard or whatever, and you see the Milky Way, then that is
That's a
dim.
good,
That's a good enough condition. You're going to see
Right.
decently the aurora. But if you can't ever see the Milky Way, then it's too bright in
It's
terms
too
of
bright.
city lights.
yeah.
Right. Yeah.
Yeah.
I will agree with that.
So you mentioned
Yeah.
Vincent about photography.
hmm
So did that photography come along your interest because of the aurora, or did you develop that sort of independently of photographing other things and said, hey, I can use this sort of as a tool to capture some of the cool sightings that I'm getting of aurora?
Yeah, exactly. Yeah, the latter is kind of what transpired there. So I guess I've always just been into sharing what I'm seeing with other people, and I think that that's sort of the essence of photography for me is you have this really cool experience outside, or whether you're just walking around, you see something interesting, you take a photo of it, and then you can kind of, I don't know, immortalize that memory in a picture and then show somebody else, hey, I saw this really cool thing, isn't this cool? And that inspires them to want to basically go see the same thing that you just saw. I think that was sort of the passion that developed, and then combining that with auroras, people obviously are interested in auroras. I guess not obviously, but from what I've seen, people are just generally interested, like, oh, there's this dancing cloud in the sky, that's really cool. Then you show them a picture of it and they're like, whoa, that looks awesome, like I want to go and see that. So
Right.
photography was sort of a big motivator for me to get out there. because it is a lot of work. You have to drive out of the city, or sometimes sitting there for hours and hours. It's cold. You might not see anything anyways, but if you have a camera, you can take a picture of what you saw. It's kind of like, proof that you did see the aurora, and then you can show it to other people and get them excited. And then, it sort of brings people into this like cult of aurora chasing. you can recruit more members, basically. So yeah, the photography evolved before the aurora chasing did for me, but it's all tied together.
Okay. Now, Vincent, this is a good transition then to show some of your work. So if you
Sure.
are able to do that.
I am ready. Yes. And before I go into my photography, is it okay if I just give a little bit of background on how the aurora is formed?
Sure. Anything you like.
Sweet. All right. So this is a little presentation I prepared, but I'm not going to go over everything in depth. But essentially, it's sort of like an aurora's 101. And disclaimer being that I'm still a student, so I'm going to do my best. But this is going to be at a pretty low level, so I shouldn't have too many missteps here. But basically, the aurora comes from the sun. It follows this path down to Earth, and there's a lot of steps along the way. And it's a lot more complicated than people think. So it's fun because we've seen auroras for thousands of years, but up until probably 50 or 60 years ago, we didn't really know where they came from. So it all starts with the sun, and we all know the sun. Obviously, it's the bright thing in the sky. It gives us warmth, life, energy, and it's what powers everything on Earth. But it's also the source of space weather, and there's weather on the ground, and there's also weather in space, which is a phenomenon that actually most people don't realize, is that space is not just this empty void. There's things going on, and those things can interact with Earth and cause disturbances and effects on the ground that we can perceive. So there's constant sources of space weather. So like a boiling pot of water or like a hot cup of coffee, the sun is always releasing this solar wind into outer space. So if you imagine like steam coming off of a cup of coffee, the steam is a solar wind. It's just constantly flowing out of the sun. And that solar wind and everything from the sun is plasma. So it's charged particles. And these charged particles can interact with other charged particles and magnetic fields and everything in outer space. And that, in turn, as I'll explain later, can cause auroras. But besides constant sources of space weather, there's also these transient events, or these sort of solar storms, which are coronal mass ejections, which you can see up on the top right. There's solar flares, there's energetic particle events, big radiation storms, and there's also coronal holes. So up here on the top right is a big explosion on the sun, which we call a coronal mass ejection. It's basically like a sun sneeze. So if the sun, sneezed out a bunch of particles, it's this big cloud that's moving out into outer space, and sometimes that can hit Earth and cause auroras. So once all those things get to Earth, it doesn't just hit our planet. We actually have a protective barrier that shields us from a lot of these things. It's called Earth's magnetosphere, and it looks like a teardrop. So the side on the front is the side facing the sun is compressed because the solar wind has pressure. So imagine you're sandblasting something. It's like the solar wind is sort of pushing Earth's shield in, so it's compressed on the day side is what we call that. And then it's elongated on the night side, which stretches into a tail. And this magnetosphere protects us from the solar wind and all the other bad things out in space. But there are some holes in which particles can get through and make it down to our atmosphere over the geomagnetic poles. So the magnetic field from the Earth, which is generated in the core, we have geographic north and south poles, but we also have geomagnetic north and south poles. Earth's magnetosphere is sort of an extension of that magnetic field out in space. And the way that auroras are formed is actually pretty well known at this point. I mean, obviously not everything is well defined, but there's this thing called the Dungy cycle, which basically describes how energy from outer space couples into Earth's magnetosphere and gets transferred into the aurora. So you have sort of this complex process, and if you want to learn more about it, you can easily Google it and find all these papers. But it's this fancy phenomenon called magnetic reconnection, where all the energy is transferred along field lines, and those particles then are kind of slingshotted around and end up over Earth's magnetic poles and into the aurora. And the aurora takes the form of these ovals that appear in both the northern and southern hemispheres around 66 to 68 degrees magnetic latitude. So just like we have geomagnetic and geomagnetic north and south poles, there's also geomagnetic latitude. So fun fact is that North Dakota is actually, I believe it's 48 degrees north geographically, but geomagnetically it's about 55 or 56 degrees north. So we're actually at an advantage in North Dakota to see the aurora, because even though we're pretty far south, the geomagnetic pole is closer to us than, for example, in Alaska or Russia. So the auroras take these ovals, these oval forms, which are called the auroral ovals. And an important fact is that there's aurora at all times on Earth somewhere. So these auroral ovals are always juiced up, but they grow and they shrink based on geomagnetic activity. So based on things like coronal mass ejections, if there's these transient space weather events, that may cause the auroral ovals to expand equatorward. So in our case, that would be to the south, since we're in the northern hemisphere. And that brings aurora down to lower latitudes like North Dakota, but even as far south as Atlanta. And there was aurora seen pretty recently in places like California. Death Valley saw aurora last month, as well as places in Utah, Nebraska, Colorado. So these solar storms can really drive aurora far south here in the US, where lots of people can see them. On the microscopic scale, so that was sort of the macro scale. So auroras form these auroral ovals, but on the micro scale, the aurora is actually a chemical reaction. So you have these charged particles coming from Earth's magnetosphere, from outer space, that hit our atmosphere, and they just don't go all the way to the ground. The atmosphere is pretty thick, so they run into these neutrals and they ionize them. So they hit these atoms or molecules and they cause an electron to bump up to a higher orbital shell, and then when that atom or molecule de-excites, it releases a photon of light, which we perceive as color. And the color of the aurora corresponds to the different neutrals being ionized. So for example, green and red are oxygen, and purple is nitrogen. And there's all sorts of colors you can see in the aurora. It basically spans the entire rainbow. And these colors are also formed at different heights. So, the chemical makeup of the atmosphere varies as a function of altitude. And depending on how energetic the particle is coming in from outer space, that can penetrate either deeper or not as deep and interact with different molecules and chemicals there.
So you can kind of get a colorful display of auroras simply because it's like layers in a Photoshop image.
Yes.
Okay.
Yeah, exactly. Yeah. Yeah. So a lot of times you have all these colors happening at once too. And this pink color, which you see at the bottom here, it says below 60 miles. This is some of the most energetic aurora that can happen, because it's actually further down in the atmosphere. So it takes a particle with higher energy to make it that far down.
Right.
And then just kind of going, now this is where my photography, you can start, well, everything in this presentation has actually been my photos, besides the nice, solar images. I don't have a $200 million spacecraft. I wish I did, but
yet.
yeah, maybe one day. But the aurora can take all sorts of different types of forms here. You have streamers and bands, swirls, curls, arcs. There's really not a good glossary of terms for auroras. It's pretty loose. So one type, I'll have a photo of it later, but one type of aurora that I've kind of coined as my own, and people have their own little affectionate terms for these things, is a cinnamon roll aurora. So these swirls and curls, sometimes they form these sort of spirally shapes, and it looks like a cinnamon roll. So there was one aurora that I saw. It was actually March 5th of 2022. I have all these dates, these really good auroral storms. I have all the dates memorized. I saw this huge spiral, and it was moving across the sky, and I was like, wow, that looks like a cinnamon roll. And I was also really hungry too. So that might have influenced
how I maybe just a little bit. Yeah,
maybe just a little bit.
But like you go to the grocery store, and if you're hungry, you went in for milk and you come out with aisle 4.
Yep, exactly. Yeah, that's happened to me too many times. So you had these discrete auroral forms, which are sort of these and they're called discrete because, if you look in the sky, it's just one aurora. Like you can clearly define it as sort of, okay, yes, this is the aurora, but you also have diffuse aurora. And what's important about these two different types is that they're created by different processes. So the Dungy cycle, which I showed earlier, is kind of what creates these discrete auroral forms, but there's more complex interactions between particles and waves and all these fancy things that create the diffuse aurora. And it's actually weird too, because the diffuse aurora is visually dimmer, but actually has more energy in it because it's at a slightly lower altitude and the particles are of different makeup. So this diffuse aurora is actually very interesting from a scientific perspective, even though it's not as visually appealing. And just to go into the science a little bit more, the aurora happens, in our atmosphere, actually in a layer called the ionosphere. And because of the way magnetic fields work and, good old Maxwell's equations and things like that, you can trace back what the aurora is doing in the atmosphere to different processes going on further out in outer space in our magnetosphere. So that's one of the cool things about studying the aurora, is that you can get a sort of window into these invisible forces and phenomena that are going on out in outer space that we can't usually observe unless we have spacecraft there. So it's a sort of visual manifestation of all these different things going on.
Now, Vincent, for the diffuse aurora,
Mm-hmm.
isn't this the type that would lead to misidentification? Because some people, they look up and it's hard for them to tell the difference between aurora or just some, cloud-like structure in the sky
Right.
and maybe scattered light from a nearby community or something. So,
Right. Yeah, that's a great point.
so what's one of
Yeah,
the things you look for to distinguish between real aurora and then, ordinary clouds?
Yeah, I would say the biggest thing with real aurora is that it's always going to be above clouds. So I mean, if there's clouds in the sky and you see sort of a glow behind the clouds, that's likely aurora. But also, the aurora does change with time, even if it looks pretty static in one snapshot. What's helpful too is to take multiple images over time, like with your iPhone or something, and if you see there's a change over the course of 5 or 10 minutes, that's likely an aurora. Also, your iPhone can usually pick up more colors than your human eye can, because our eyes, essentially, they suck at seeing in the dark. So auroras always have a green color, but it's usually not visible to the eyes unless it's bright enough. So taking out your phone and just seeing what it can see, if it's green, then it's an aurora. That's pretty obvious. So that's what I would say. If you don't see like a characteristic, band or arc, you just see this glow, try and see if you can get a better picture of it with a phone or a camera.
Right. So if you stare at the sky, for example, near overhead, and you see a lot of the streamers like features, and they're
Mm-hmm.
changing over a very short time scale, like order of just a few seconds, then that's got to be aurora. It can't be ordinary clouds moving.
Right.
Like that.
Yeah. No. Yeah. Clouds don't move that fast unless you're in a tornado or something.
Right.
Well, aurora don't
yeah.
usually move quite that fast.
They can, yeah.
but they
They
can.
Yeah,
definitely can.
Can.
Yeah.
Absolutely. Yeah.
Oh yeah. 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 Auroras can be very,
Pretty
very,
dynamic. Yeah.
very dynamic.
When we're thinking about a misidentification, I know there's been occasions, especially in the wintertime here in Grand Forks, where when the atmosphere has a lot of ice crystals suspended in it, that you'll
Mm-hmm.
get like lights from, let's say, car dealerships that shine upwards, essentially.
Yep.
You'll get these
Right.
light pillars.
Light pillars.
And because of the changing, I guess, in the ice crystals, their orientation and so on, and their
Mm-hmm.
movement, that can give a sort of flickering-like appearance that at
Mm-hmm.
first can be very hard to distinguish between a big aurora event that's happening or whether it's a very
Mm-hmm.
local phenomena as we described, right?
Yep. Yeah. That's important too, is trying to distinguish between those light pillars and aurora. I know there was one time in Grand Forks a couple of winters ago where there were these huge light pillars, and of course it was after a hockey game, so everyone was outside, and I think I got about 20 messages that were like, "Hey Vince, is this the aurora?" And I had to be like, "No, nope, not aurora." And an easy way to find out if it's aurora or light pillars is obviously if you move further away from the town. If those light pillars go away, then it's not the aurora, because the aurora, she'll get brighter as you go away from town because it's getting darker in the sky.
Right.
But also, yeah, usually those light pillars are pretty bright too.
Well,
and almost extend from the ground, sometimes from the ground, and they're perfect, vertical spikes.
and they're also
And
dependent on the angle of observation. So if you change your
right, that
angle any
too.
amount, they should disappear.
Yeah, in some sense, if you
Right.
think about it, this is a new phenomena since humankind, used electricity to make artificial
Right.
lighting. Like this never
Mhm.
existed before in that sense, right?
Right?
So
No, yeah, that's true.
yeah, so here's a totally artificial sky phenomena, and
Yeah.
you can go around as a photographer and clearly photograph this phenomena,
Yep.
right?
Mhm.
Photograph the light pillars and so on. So this otherwise would never have happened if it wasn't for light pollution in some sense, electricity, right?
Yeah. Yeah.
Yeah, yep, yeah. Light pillars are a big false flag of auroras nowadays. I see it all the time in Facebook groups too. So it just takes a little bit of critical thinking when you're out there and just checking off the boxes or crossing out the different criteria to figure out, okay, am I actually seeing the aurora? And it's a lot harder to do that when you're in North Dakota because the auroras are usually pretty dim. Whereas here in Alaska, it's very obvious. Like you'll see a huge, band across the sky that's moving and rippling, and you're like, whoa, that's definitely the aurora. But in North Dakota, I mean, there's been times where I've questioned myself too, as somebody who I would consider myself pretty expert in identifying auroras. But there's been times where I've, thought to myself, yeah, I wonder if that's a cloud, or is that an aurora? I don't know. And I've had to take a photo of it. So
Now
yeah, if
I
you have a camera, that'll seal the deal essentially. But,
now I will point out there is a phenomenon called noctilucent clouds, which
Mhm.
is related to aurora actually. Not the
Mhm.
same thing, but it is related. So that's something but those will usually be blue or bluish in color
Yeah, yeah, and those usually disappear too as the sun goes
as the
down.
sun goes down. Right.
As it goes fully down, and they don't usually happen during the winter either.
Good
Those are
point.
exclusively a summer phenomenon.
Good
So
point.
Yeah.
yeah,
And so the other thing is Robert mentioned, if you're in doubt, like the difference between light pillars and aurora, just changing your location can
But
make a big difference because we're so
yep,
close this thing that it's not like aurora where if you change like by 2 miles, if you're in the same kind of lighting conditions, you're not going to really see any difference at all. But in a
hmm
city, that could make a huge difference, right?
right.
hmm right. Yeah, and one big misconception too is that the aurora is this localized phenomenon. I get people all the time that come to me and they say, "Hey, I'm in Grand Forks. How's the aurora in Grafton, or how's the aurora in Moorhead?" It's like it's the same. The aurora is huge. It's like you're looking at a huge thunderstorm off in the distance. If you move 10 miles east or 10 miles west, that thunderstorm is basically going to be in the same spot.
Right.
The aurora doesn't change that much on scales of even 100 miles. You have to go pretty far to see differences in the auroral oval. However, when it comes to substorms and these dynamic auroral structures that are a lot smaller and localized, then you can get some differences between locations. But in general, if you see something in the sky, you could call up your friend in Duluth or call up your friend in I don't know, Dickinson or something, and say, "Hey, are you seeing this cool pillar?" And they would say, "Oh yeah, I'm seeing it too." I've actually had those phone calls before with some friends out on the North Shore of Minnesota. We're both looking at the same aurora basically, and we're over 300 miles apart. So the aurora is a huge phenomenon.
Okay.
So the other thing you mentioned, misconception. So what's been your craziest thing that you've heard about the cause of aurora to begin with? Can you share some of that with us?
Yeah,
No
I don't know.
names.
Yeah, no names. Well, there's too many names. So um, I guess I don't know if it's the craziest. Well, okay, I guess I can go into two different things. There's the craziest, and there's also the most widespread, but also not really. So I should also preface this with a lot of the misconceptions around auroras and also space weather too stem from society. There's this whole field called astrosociology where the Hollywood movies, for example, or pop culture has taught us to believe a certain way about science, and that unfortunately indoctrinates people into this false reality where they think a certain way, but it's actually not their fault. It's just what they've been taught. But
Right.
the biggest misconception I would say is that auroras happen when it's cold and it's a reflection of the ice, like sky light or something off of ice in the Arctic, and that causes like a reflection into the sky, which we see as aurora. That was actually the belief. That was like the scientific belief for a long time,
Wow.
like hundreds of years ago. So I've met people who still believe that because they just aren't up to date with the science. So that's one misconception, and not really, a dangerous one either. It's just, that's just what they believe, and it's still a natural phenomenon in that case. But I get a lot of people who think that the auroras are created by HARP. So HARP is a facility here in Alaska, actually, which UAF helps out with. But they think that it's a man-made phenomenon, and you can basically turn them on or off. I've had people that have come to me and said, "Hey, can you flip the switch tonight? I'm out chasing in Fairbanks." I'm like, "Hey, that's not how it works." Hate to break it to you. I wish I had a switch, but some people think it's this. You can just charge up the atmosphere with a bunch of lasers or radio waves and create these, widespread phenomena. And actually, HARP can create artificial aurora, but only in like a very, very small area. But yeah, I mean, there's a whole lot of other ones too. But I think those two are the biggest in terms of what I see on social media and what people ask me about are, oh, is it only because it's cold? It's because you're in the Arctic. No, you can actually see auroras all year round. So you can cross that off the list. And then if it's HARP, well, no, it's not HARP because, it doesn't have the power to do that. That'd be insane, right? So, yeah.
Now, I know there's been experiments that like NASA's been involved in where they launch sounding rockets from Wallops Island, Virginia, I think. And they would deposit material into the upper atmosphere, and you see that man-made, if you like, or human-made aurora to get an idea of how it functions to try to improve on our understanding, right?
Yeah, so I mean those rockets do exist, but the aurora that they create is much different. It's like little clouds, like little. So I did some research on. There was this mission called CRX-2, which was a sounding rocket out of I believe it was Andøya spaceport in Norway or something, or maybe it was in Svalbard. I'm not sure, but what they do is they have these sounding rockets that are filled with tracers. So usually it's barium, strontium, and TMA, which is trimethyl aluminum. And these tracers are launched or are basically dropped out of the rocket once it reaches its maximum height or along the path of the rocket at varying heights. And these tracers are, they photoionize with the sunlight, so they start to glow. They expand. It's like these canisters that explode. And then based on the neutral winds up in the thermosphere, which is sort of in the same region as the ionosphere, these clouds start to expand and they drift either, north, south, east, west, whatever. And then there's also, there's these neutral tracers. There's also these tracers that are affected by electric fields. So they will drift maybe the same direction, maybe opposite directions, but they give us an idea of what's going on in the thermosphere, because there's no way that you can fly a satellite through that area of space because it's too dense. The satellite would just crash back down to the Earth. So the only way to really study the aurora in situ, or the atmosphere where the aurora takes place in situ, is with sounding rockets. So yeah, those auroras, if you will, they're usually different colors too. Like I think the barium tracers are like a dark blue, and they only last for a few hours. So yeah, but they're cool. I've actually never seen one, but there's a rocket. There's all these rockets all the time up here in Fairbanks. I think there's going to be one. It's called the Awesome rocket, I believe, AWSOM or something. That's going to do another artificial aurora experiment, I think, next year. So I'm going to try and help out with that. But
Now, just in case somebody doesn't know, I'm going to ask the question: what is a sounding rocket?
yeah, so sounding rocket is basically a lot of them are actually retired, like World War II missiles. The exact, models of the rocket vary, but there are these 1 or 2 stage, sometimes 3 stage, maybe even 4 stage rockets that are about the 30 to 40 feet long. They launch into the upper atmosphere. They go. It all depends on the mission. There's different heights and distances that the rockets travel, but they take around 5 minutes to go from the launch to the to when they crash back down in the Earth. They don't stay in orbit. They don't even really go into space, but they go far enough into the atmosphere where they can fly through the thermosphere and the ionosphere, which is the place where the aurora takes place. And they have instruments on them which can measure magnetic fields, electric fields, particle precipitation. So all the particles from outer space that I was talking about, they can hit the rocket, and we can record how many are hitting and which direction they're coming from, and then that gives us an idea of all the dynamics going on up there. And they've been used to study the upper atmosphere for probably 50 or 60 years, and they're the most popular way to figure out what's going on up there. The satellites, like I said, even though it's almost in outer space, the atmosphere is too dense for a satellite to remain in orbit in that zone for maybe more than a couple of weeks. So there's no point in sending a mission up there, really. So they just do it with sounding rockets. It's a lot cheaper.
Yep. Okay.
Well, it just tells you then there's a lot of stuff we still don't know in terms of nitty-gritty detail about the aurora themselves. Is that fair?
Oh yeah, yeah. There's there's so much we don't know. And what's cool about the aurora is it's fascinating from so many perspectives. Like, it's beautiful. Obviously, I just love to go out and look at it. And then there's the photography aspect of it too. Like, how to capture the aurora and share it with other people is a whole other facet. And then there's the scientific perspective, which is what causes the aurora. And we know what causes the aurora, but we don't necessarily know what causes specific types of aurora. So like these substorms, that has only recently been figured out as to what's causing them within the past 10 or 15 years. And then there's, even more processes beyond that we just have no idea, how they work. And then auroras also affect things on the ground. So, auroras are part of space weather, and space weather, while it creates the auroras and is cool, it's also detrimental to infrastructure. So when you see a huge aurora in the sky, chances are you have a lot of GICs, or geomagnetically induced currents, flowing in the ground, which can cause disruptions to power grids. And you also have scintillation in high frequency signals. So if you're a GPS operator or GNSS operator, auroras can be a big pain because they cause your signals to drop. So auroras are cool, but they're cool for many reasons.
Well, having also studied some planetary science, they're also a good way of looking at the magnetic field, which in turn can tell us what's about processes going on in the core. So there's a lot of things you can get your hand on by simply studying and knowing what the aurora is doing.
Well, Vincent,
Jupiter has auroras, Saturn, I think most planets do. So,
yeah, I was just going to mention that they're not just found here on the Earth, right? There's other locations that have an atmosphere in our solar system. We've seen aurora. So, as Robert mentioned, you could use that to determine properties about other bodies in our solar system, other than the Earth.
Other than the Earth,
Yeah.
I mean, pretty much anybody that's got a magnetic field is going to produce aurora in some way.
An atmosphere,
Well,
and
and an
magnetic
atmosphere,
field, right?
Yep.
Because even Mars, I think they observe aurora on Mars too. So
I think Mars has sort of a crustal magnetic field, so it's in little patches, and you can get this sort of air glow and localized auroras there. Yeah,
and even a body that doesn't have a permanent atmosphere like Io, they've observed aurora on during volcanic eruptions, which are fairly constant in Io. But neat stuff.
now, when I always think about aurora, sometimes announcements are made by the mass media. There's going to be a big aurora display tonight. Everybody should get out and look. And it's almost like comets coming, right? It's going to be the brightest comet in 500 years, and then you can't even see it, with your unaided eye or something, right?
Well, that and a lot of people really just don't understand that even a big display is still pretty dim, and you've got to get out of town. You really do.
Yep.
But there's even been situations where they call for a big display of aurora coming up, let's say tonight, and it turns out it's a dud. So clearly, we don't know everything in terms of what sets those off, right?
Yeah, so the forecasting of these big auroras usually happen because of these coronal mass ejections, for example, and they're just really hard to track. Obviously, once they leave the sun, there's no satellite in between that can say, okay, yeah, it's coming, but, watch out. The most we have is something at L1, which gives us maybe an hour, 45 minutes to an hour heads up. And then once it gets there, it still has to hit the magnetosphere, and there's so much that can happen there too. So it's the space weather forecasting part that's just not there. In fact, a lot of times you ask scientists about this, and they say, space weather is where terrestrial weather was at in the 60s. That's essentially what we're dealing with. So we're flying blind, during a lot of these events.
I will disagree with you a little bit. We get a little more warning about coronal mass ejections, or CMEs, than that, because they can only happen if they're pointed at, they're on our side of the sun.
Yeah.
So, we can see, is that one going to hit us? And
you can see, you can see them coming off the sun, but also just the way that the way that the instruments we have work, there's still a lot of ambiguity.
Absolutely.
The models, the models work pretty well, but they're just models. A lot of them don't even take into account magnetic fields. They're just hydrodynamical models instead of hydrodynamical models. So if you have a lot of stuff going on, you have a lot of stuff going on in interplanetary space, it could deflect one or the other. Yeah, it's this whole thing. But we're doing a lot better than we used to, for sure.
And then on top of that, we're a moving target. So
yes.
Yeah, the other thing I wonder is, if you play devil's advocate a little bit about this, is you could get the same influx of charged particles, let's say 20 different times, and they would produce not always the same type of aurora activity.
Yep.
Right. Yeah. There's just so many things going. I think the biggest thing that I've realized since I've started school and just kind of got into this a little bit more is the more you look into it, the more you realize that there's so much we don't know, and that, first of all, no two auroras are ever created equally, but no two geomagnetic storms ever produce the same pattern of aurora. There are setups and patterns that you can say, okay, well, we see this in the solar wind, we should get an aurora like that, but there's 80, 90, 100 different phenomena going on at once that you have to take into account. So it's really tricky, which also makes it really fun too, because if we had it all figured out, it wouldn't be such a thrill to go out and
where's the fun in that?
Right. You have to have some duds, right?
Right.
That's what makes it hard. It's that we don't have all the information. So that's why I like aurora chasing, because it's not as easy as go outside and look up. You have to know a little bit about what's going on.
Now, this whole topic of space weather, that's really ballooned in the last couple decades, and I think a lot of part of that is probably our emphasis on satellite technology, whether it's for the military or otherwise. And so I think people appreciate more so nowadays of how maybe vulnerable our systems are to space weather. And so we want to be able to keep very accurate track of what's going on with our sun and the kind of the region in between the Earth and the sun, to say, here comes a large event. Chances are it's going to do major damage to our satellites. Let's start shutting some of them down so we can try to prevent some of that damage from occurring and minimize the time it takes to get up and running again after the event occurs. Right.
Well, to me, one of the worst things that can happen, these particles, folks, are electrically charged, so they can send an electric signal through electronic components. And the real thing is it can trick the satellite through those electronic signals into thinking it was given an order to turn around. Well, that satellite is now gone, because we can't even get a signal to it to say, hey, turn back around. And point towards us.
Well, you know something worse, Robert?
What's that?
Imagine you had a satellite and said, turn on that laser beam and fire it at a certain country.
Those satellites don't exist.
Sure they don't, Robert. But you can envision all kinds of horror that could happen.
There's a story in that.
Here's some real horror. You ready?
Huh?
All of the satellites go out. We have no internet for a long period of time. How would we do our podcast, Robert? You see?
The real dangers.
The real dangers.
And that is, and the other thing you think about is, where does it all come from? You can tie it all the way back to the sun, as you mentioned already today.
Yep.
And so how well do we understand our sun? And well, we only have the one thing to look at, right? We have our sun and we study it, but we're studying things after it occurred and try to understand why they occurred rather than trying to understand what's going to happen in the near future. So what can you do to get around that? Well, a lot of times what we do, of course, is we look for other stars that are as close to the sun as possible in terms of the type of star.
Right.
And the scariest thing, and I like to tell this usually to introductory astronomy people just to let them know that, hey, there's cool things that happen in space, is that when people study stars like our sun, there is a fair fraction of those stars that are really, really active, so that you would not want our sun to be one of those stars, and yet it's the same type of star. So that always begs the question, will our sun at some point in the future, now that could be 100 years from now or 1,000 or 10,000 years from now, or it could be tomorrow, will our sun enter this new really hyperactive phase? And that could cause a lot of changes here, affect us greatly, right?
We had that happen in the 1800s.
Yeah.
Was called the Carrington event. So.
Yeah, and what happens if we get an event that's like 1,000 times more powerful than the Carrington event?
Right.
And the Carrington event wasn't even, well, they actually do know based on ice cores and just even more recently than the Carrington event that the Carrington event is not the most severe solar storm that we've encountered. So yeah, there's definitely bigger events out there that could happen.
Yeah. And for those that don't know, the Carrington event caused auroras to be seen as far south as Cuba and set telegraph wires due to those induced geomagnetic currents, set telegraph wires on fire. So that was we're sitting there saying ice cores have shown us that bigger events have happened. Yeah. That was a big event. If something like that happened now, we're cooked. Our power grid is gone.
Yeah, well, imagine electronic equipment we have now, and they'd be exposed to all of this. And our reliance on technology, at least for where we live, is so huge that makes us, from one point of view, that makes us very susceptible to these kind of things that could possibly happen.
Yep.
Yeah, I will say though that there's been outages since the Carrington event, modern events, like there was one in 1989, the Hydro-Quebec power system failed for multiple hours, and we have learned a little bit. So I think if the Carrington event were to happen now, we would probably be okay. It wouldn't be the apocalypse that a lot of people think. It wouldn't be good.
Right. It wouldn't be good.
Obviously, it wouldn't be good. Wouldn't be good, but we wouldn't all die, which is the main thing. So
well, that would kind of give you support for the space program, because you'd like to have satellites, as we alluded to already, in orbit around the sun that are a lot closer than Earth, that are in the right orbit, so they could let us know what's going on.
Because we can save just about everything by simply powering down for a few hours.
Yep. Yep, and they already do that. Yeah, there's certain parts in even just without any space weather. There's a South Atlantic anomaly, for example, where there's essentially a hole in our magnetic field over like South America, where they power down satellites, some satellites when they pass through that area. So yeah, that's a strategy that works. So.
Yeah, you're thinking, you can imagine a ring of satellites that's on an orbit like Mercury's orbit.
Right.
And you string them around because they're moving in an orbit that's clearly going to be faster than Earth. And so you have enough of them that you're always monitoring the side of the sun facing the Earth. And now, and light traveling from the sun, it only takes a little over 8 minutes to get here. And these particles, since they have a mass, they'll travel a little slower. But still, they're here in several tens of hours.
Yeah.
So it's
the energetic ones are.
So you're not like you have months to play here, right?
Oh, no.
Yeah, but they could give you a heads up to say, okay, you've got 10 hours to shut down your most vulnerable satellites, and then we'll power them up later when the event goes away, when it's over with.
Right.
There you go.
Yeah.
So folks, the point is, we want more of us studying these things, and you want to put more money into studying these things. So,
it gives you a sense of something that at first seems so benign and not affecting me personally, the Northern Lights, could actually have a major, major effect when it's related to the solar activity. Right. It can kind of almost destroy the way that you live for a period of time if you need to, stop everything for a week or so. I mean, the financial industry, if you shut down all electronic banking and stuff for a week, right, when the systems are down. I mean,
Hmm.
just a week is enough to cause major, probably just half a
Oh
day
yeah,
is enough to cause
Right.
major financial chaos, right?
There you go.
right. Yeah, I think the biggest question mark right now is, what will happen if we get another big event? How will we respond? Because we haven't had a big event for 40 years almost. So it'll be interesting to see what happens, because we've kind of been in this quiet period for a while. So we'll see. But yeah, I mean, if you want to get into a science that has a lot of real world, implications, I mean, the auroras, are kind of this manifestation of space weather, but space weather and space physics as a whole is very much tied to operations. The military has a lot of ties with even the aurora, and using it to sort of predict where you're going to have HF signal issues and dropouts. And then anything with space travel, you need to know what's going on in the solar system with space weather. It's a huge field. So
Well, a big storm will ground aircraft
Yeah.
because the high energy particles will reach deep enough into the atmosphere to be a problem for airplanes.
Yeah, you always worry about flights over the poles are exposed, especially.
So
yeah, and there's been times where airlines will divert polar flights due to radiation storms. And NOAA, SWPC, Space Weather Prediction Center, which is kind of I don't want to say the world's forecasting office for space weather, but definitely the U.S. Some of their major customers are agricultural companies because of the high precision GPS that's used in farming, aviation industry, military, obviously, even a lot of drone operators too. They're starting to do precision drone, like Amazon's drone delivery systems, even medical drones now. So yeah, there's a huge need for better forecasting and more science.
So the Space Force must have a part of that that's devoted to space weather. It's got to, right?
Mm-hmm. Right.
It's
Yeah.
just
Exactly.
such a natural thing to do. Now, Vincent, I noticed you have a movie here you like to show. So a lot of times
Yes.
you can see a lot of cool stuff instead of looking at single images. Actually,
Yeah.
see things moving. So
oh wow.
Yeah. I guess I can just run through this a little bit. So these are substorms. So when the aurora is really going, it'll sort of, I like to call it an aurora explosion, where it sort of turns from this quiet arc to this really dynamic and fast moving, basically streamers everywhere, and it's racing across the sky. So this is a time lapse, about 15 minutes at I think 3 or 4 second cadence, where you can see a quiet aurora just totally erupt into this thing that's just wild.
I was
And then
yeah, go ahead.
oh, sorry. Well, I was going to say, and then this is just a little plug, is that these auroral beads that you see oftentimes before substorms are actually what I'm doing my thesis on here at UAF, and trying to figure out what they mean, because oftentimes before the aurora explodes, you see these little bead structures forming on one of the arcs. Like you can see here, this is an all sky image. And you see these little dots that form along the arc, and these propagate along, and then they form this this poleward expansion is what we call it, and then that turns into the substorm.
So what's the spacing between the beads? Is that related to the magnetic field line spacing, or?
Yeah, it's all So the spacing between the beads, the growth rate of the beads, so how fast they brighten up, how big they are, physically, and also where they take place in the sky, the magnetic latitude, longitude. Those are all related to the different phenomena that govern their formation. So essentially what plasma instability is forming the beads is the main question right now. So, and also whether or not these beads are formed by something in the magnetosphere or something in the ionosphere, if it's a local phenomenon or if it's a global phenomenon. Because something in the magnetosphere, if it happens out, far out in space, it's going to travel along both field lines and travel to both the north and the south geomagnetic poles. And they found that the beads are sometimes not conjugate, which means you can see beads in one hemisphere but not the other hemisphere, which is really interesting.
Oh wow. Okay.
Yeah.
That's interesting.
So how often does that? So I'm looking at the image sort of in the bottom center. So how often would that type of feature be viewable during an aurora display?
That's one of my research questions, actually.
Okay.
So you don't see the beads before every substorm. You sometimes see beads without a substorm. You sometimes see, there's all these different scenarios. So the consensus right now is that, if you have a substorm, you have beads, but that's not always true. And that's what I'm trying to prove with statistics right now, but also, later with like theory and, actual, physical understanding of, why do we only see beads sometimes? Because you see beads in about 90% of substorms. But there's 10% of substorms which don't have beads. And then there's actually a lot of bead events that don't lead to substorms. So you have these beads form and it looks like the aurora wants to, go, but it never does. It's like, it's just about to go and then it pulls back or something like that. So it's kind of an interesting, interesting phenomenon. So.
I've got to make an observation that they really remind me in your movie of solar flares, which are often caused by magnetic reconnection. So could those beads have something to do with reconnection phenomena?
Yep. Yeah. So reconnection in the magnetotail, which is, way duskward, or I guess on the night side of the Earth, when those field lines reconnect, particles then travel towards the night side of Earth, and that's how you get aurora. That's how you get a lot of these discrete auroral features. So, magnetic reconnection definitely plays a role. It's just a matter of how much reconnection, or
how much of it,
how much of it translates to auroral beads, and whether or not there's other processes too. Like, you also don't need reconnection to create aurora. You can have aurora that comes from the radiation belts, which are closer to Earth, and you can get energy inputted into the radiation belt that excites those particles enough to the point where they end up in our atmosphere. So that could be a possibility too.
Yep.
There's so much going on with the aurora. It's just hard to explain it all in 1 hour, but it's really fascinating. Oh, and then this is just so we already talked about this, but aurora chasing's cool. And then here's some stuff from North Dakota. So what I want to kind of draw your attention to is the one on the left, the top left. That's actually a steve. So this is a phenomenon that's unique to mid latitudes, actually. So people in Alaska, we have it pretty nice with auroras every single night, as long as it's clear. But we really never get steves. So steve, that's actually the name of it. It's called strong thermal emission velocity enhancement. It was discovered by aurora photographers, and it was a phenomenon that it's been around forever, but scientists didn't think you could actually see it with your own eyes. They thought it was subvisual. So when photographers started showing the scientists, hey, we can actually see this, it was like, whoa, this is a lot different than we expected. So this is a picture of a steve I took all the way back in 2019. So this is like one of my first aurora chases ever in North Dakota. Was this image here, just near Emerado. So pretty close to Grand Forks. And the steve is this purple whitish band, and then these little streaks are called the picket fence, which is actually not steve. It's associated with steve, but it's a totally separate phenomenon too. And scientists don't really know how this steve occurs. It's an area of study right now.
Cool.
So I guess it's fair to say, one of the things we do in science is especially when we're trying to understand something in general, is to make sense of it from a point of view of like classification.
Mm-hmm.
Right.
And so that's one of the things that seems like a lot's done in aurora science, is to classify all the different types of features and shapes you can see. And then ultimately you want to understand why are they the shape that you see.
That's
right.
It. Yep.
Yep.
And interesting things happen at the interface. So
Yes.
things are changing from one thing to another.
Right. So I got a nerdy type question, Robert.
Okay.
Sure.
So as one nerd to two nerds. But during the aurora activity, can you get sensitive enough magnetometers on the ground that you can actually detect fluctuations in the magnetic field?
Oh yeah. Mm-hmm.
Because that would be kind of cool to kind of relate that to the type of aurora that you're seeing.
Mm-hmm. I knew that you could like hook up a speaker, the power leads to like a barbed wire fence, and hear the aurora going on because of the radio signal that it's giving off.
Right. So that barbed wire fence will act like an antenna then.
Mm-hmm.
Mm-hmm.
Interesting.
Yeah, both of those are true. Yeah, you can definitely use magnetometers. That's probably one of the most common tools to study the aurora is using magnetometers and looking for fluctuations, especially when you have a substorm. You'll see the magnetometer go like this, and then it'll just, go off the charts almost, and then settle down again. But even with Steve, you can see it in magnetometers. So yeah,
Cool.
it's pretty cool.
Because you can imagine you have these things like remote, so you're not touching them, you're not getting by with
Right.
like the metal from your keys in your pocket is going to influence
Right,
anything. 'Cause
right.
I assume they're extremely sensitive to the ambient
Yes.
magnetic field,
Yes. Yep. Yeah. You want them buried underground and hopefully not near any train tracks or
right?
or anything like that where they're rumbling around and stuff like So
Right.
Nobody's
yeah, they're super
twirling their
sensitive.
twirling their
Yeah.
car keys on a lanyard or anything. Yeah.
Yeah.
Yeah. Yep.
Yeah.
Well,
Yeah, it's about time, unfortunately. So this has been interesting, but
Yeah. There's so much. There's so many pictures and stuff that we didn't go through, but yeah, the auroras are always here. So and if you want to learn more, I have social media and that sort of thing, so you can check them out. But
yeah,
Cool.
we always have
tons of things.
we can always have you back too, Vincent, to
So,
continue this
that's true.
discussion. Especially,
Yeah, we could make this a 4-hour episode if we wanted.
well, I'm thinking, in the future, if some kind of strong aurora activity occurs, then maybe we can get you in after that to show us
Sure.
what you've learned.
yep.
That'd
Yep.
be very interesting. So, as Vincent mentioned, he did come to UND to do his bachelor's degree in physics. So, if you're interested in studying physics, if you like to study the aurora, for example, you don't
Right.
need to run off to Alaska. You can just run to UND
Yep.
and at least get
Yep.
your background in physics and mathematics. So then you'll be able to use those tools when you go elsewhere to do more in-depth study. So, as we always like to promote, if you're interested in higher education, even if you live on the other side of the earth, of course, you can always jump onto our online programs that we have and learn that way. Or if you're around here and can make it to campus, we'd be happy to meet you.
Show you around, discuss anything with you. So introduce you to
Yeah,
some
UND was
students.
great for me, and I look back on that with so many fond memories, and really was the place where I cut my teeth on all this stuff. So can't
Excellent.
recommend it enough.
Oh, it's nice to hear that you appreciate UND, and I know all of us here at UND greatly appreciate you as well.
Indeed.
Okay. Now, our next podcast would be next Tuesday, October the 17th at 3 p.m. Central Daylight Time. And we always leave you with a quote, Robert. Today's quote is from William Shakespeare.
Woohoo, Shakespeare.
And it's actually related to aurora, so it's hard to dig around to find some written material from William Shakespeare. And by the way, who was William Shakespeare? That's something we could use for a different podcast, right?
Yep. On a different subject altogether.
I actually, that's one of those mysteries in life. Who actually was William Shakespeare? But what he said that related to auroras is this: "For night's swift dragons cut the clouds full fast, and yonder shies aurora's harbinger, at whose approach ghosts wander here and there, troop home to churchyards." Thank you very
Excellent.
much for listening.
Thank you, folks. Y'all have a great day.